All right, go and have your homework out if you would, please. And your book's open to page 92. Book's open to page 92. Trust if you're watching on YouTube, you did well on your test, just as these students did. And your homework for last night was to do page 92, questions 1 through 5, answering those 5 questions. Let's go and take a look at that. Good, and good. All right. And diving into a new chapter now. This to me is where physics really gets going. We've been looking at some different things with matter and things like that, but now we're starting to get into movement and remember we said the 5 branches, if you will, of classical physics. We had mechanics, thermodynamics, light, sound, and electromagnetism, right? None of that have we covered yet. So it's kind of a cross between chemistry and physics. Now we're really getting into physics. So this to me is where physics really begins to get fun. Not that we haven't had some fun heretofore, shooting rubber bands at people and whatnot. Number 1 says define rectilinear motion. Audrey, what did you have?
Rectilinear motion can be defined as translational motion along a straight line.
Excellent job. Number 2, what's the difference between speed and velocity? What did you have for this, Kendall?
Speed is the distance an object moves per unit of time, and velocity is the speed in a single stated direction.
Very good. Number 3, what are the 2 aspects of every vector, Michael?
The 2 aspects of every vector are magnitude and direction.
Very good. Number 4, why is average velocity independent of the route taken, Audrey?
Average velocity is independent of the route taken because it's not a vector and its magnitude is constantly changing.
What did you have for this, Kendall?
Average velocity is independent of the route taken because it doesn't necessarily go in a single direction with a constant speed.
But why does it not matter what route we take? Michael, what did you have for number 4?
The average velocity is independent of the route taken due to directional changes.
Yeah, we'll talk about it. All right, number 5. What is the difference between distance and displacement? Let's go back to Audrey.
The difference between
She gets all chipped up.
distance and displacement is that displacement is instead a straight line distance between 2 points.
Say that one more time.
The difference between distance and displacement is that displacement is instead a straight line distance between 2 points.
Like instead of what? You said instead, and I was waiting for a contrast. And maybe I didn't hear that right. No, you did say instead. So you did a good job defining displacement. What did you have for number 5, Kendall?
The difference between distance and displacement is distance is defined as the magnitude of displacement between 2 objects, while displacement is the distance between 2 points in a straight line.
Okay, that was better. Yeah, we'll take that. All right. Go and turn in your books back now to the beginning of the chapter, page 80, and in your notes. As we get started with chapter number 6, we're going to begin a unit, unit 2. So unit 1 was all about matter, introduction to physics, you might say, making sure we have a cursory understanding of how matter behaves. So as we talk about energy and how it relates to matter, we've got a good foundation. Now we get into the meat of physics with a chapter on mechanics. Go and get that term in your notes if you would. Mechanics is simply the study of motion. Mechanics is simply the study of motion. We're going to be talking about things that are moving for the rest of this semester and on into next semester a little bit as well. So the first month or so of quarter 3, we'll still be talking about motion. Spend a lot of time talking about how things move, why they do what they do, how does this motion work, how are things calculated, and we'll be doing quite a bit with that. Our study of mechanics, though, is really going to begin with a kinematic look. Go and define that term here, kinematics. Kinematics. Kinematics is the study of motion with disregard to the causes of motion. It's the study of motion with disregard to the causes of motion. So if Audrey is falling off the edge of a cliff, all we're concerned about is what is her motion? How can we describe her motion and calculate properties and truths about her motion? We don't necessarily care why she's falling off the edge of the cliff. Kendall's standing there at the top with an evil look on her face. Some people, you think they're your friends, you just don't know them as well as you thought, huh, Audrey? Thank God for that tree branch, right? But anyway, going back a few lessons ago, we got you down safely somehow, I seem to recall. But anyway, kinematics doesn't look at the cause of the motion, right? A bullet flies past Michael's head. We can do all kinds of calculations about the motion of the bullet. We don't necessarily care about what caused the bullet to fly past his head. We're just disregarding the causation of motion. That's where we're going to begin with this look, is we're not so much looking at why the motion happened or what caused the motion, just looking at the motion in and of itself. As we look at motion, there are different types of motion we'll look at this school year. But the first one we're going to talk about is something called translational motion. Translational motion. Translational refers to a change in position. So that's what translational motion is. Motion that results in a change of position. If Michael decides he wants to sit in the front seat of the classroom, and I say, Michael, move, and he turns sideways in the desk, has he moved? Well, he has, but I was referring to translational motion, right? If I tell him to move, what I'm intending for him to do is move from the seat he is in to a different location, right? His location would have to change. For instance, we think of Enoch in the Bible, remember? He was one of the two guys who never died. Instead, the Bible says that Enoch was, in Hebrews chapter 11, by faith, Enoch was translated, that he should not see death. And he was not, for he was translated. God translated. What does translate mean? Your name is no longer Enoch. It is now Enochos. No, that's not that kind of translate. Translate means he was on earth, and then poof, he's in heaven. His location changed, right? So there's different types of motion. For instance, we could have oscillatory motion or vibratory motion, right? Where I shake my hand back and forth. Well, does it ever quite change its position? Well, yeah, but then it goes right back to where it was, right? We could have rotational motion where I'm just spinning around in circles slowly because I'm old. And then I go the other direction to reset my brain so I don't fall down. Something was happening the other day. I made the mistake of finishing early in my computer applications class. Never finish early in a junior high class, ever. But I did. That was wrong. And there are spinny chairs in the computer lab. Now, be honest, how many of you have wanted to spin around and around and around in the chairs, right? But as a general rule, for the record, we will say that you exercise restraint and demonstrate maturity and choose not to spin around and around and around. Oh, Michael can't nod his head. Okay, well, anyway, 7th graders, well, no, we even had an upperclassman in there for that class doing the same thing. They were spinning around and around and around and around. I was getting dizzy just watching them. I was like, okay, stop doing that before one of you throws up. And inwardly I'm thinking, stop doing it before I throw up. Anyway, but we could spin around and around. Well, as I spin around and around very slowly, my position isn't changing. I'm still moving, right? There's still motion, but it didn't result in a change of position. But if I walk all the way over here to this wall, that's translational motion, because I ain't in the same place I was. Make sense? It's translational motion. Two types of translational motion that we could look at. One type of translational motion is called rectilinear motion. Rectilinear motion. Rectilinear motion is motion along a straight line path. Motion along a straight line path. So when I walked a moment ago directly to that side wall, I was in a straight line. Does all motion have to be in a straight line? Certainly not. Oftentimes we see motion that follows a curved path, and this would be called curvilinear motion. Curvilinear motion. And that definition is almost more obvious. It's motion along a curved path. We are going to, as we begin our study, focus on the easiest of all motions to describe, and that would be rectilinear motion. Translational motion results in a change of position along a straight line path. Takes out a lot of the extra nonsense to have to think through. So we're going to be assuming rectilinear motion as we begin our study. Now, as something moves, one of the key pressing questions inevitably is, how fast is that thing moving, right? For instance, Michael's walking down the hall, or Michael is traversing the halls. Well, if he has a pass, he's probably moving very slowly. If he's dreading an English test, he probably goes more slowly. If he has little time and there's no pass, he might move more quickly. Of course, he would not run because he's mature and knows that he ought not to run in the hallways. We're working on our junior hires still on that, right? But how fast is he going, right? How fast is an object moving? A baseball goes flying through the air. That's always one of the first things they announce on the broadcast. That was 109 miles an hour off the bat. Why? Because we care about things like that. Whoa, that's really fast. And then that was only 74 miles off the bat. No wonder he ran out the throw to first. Oh, that was really slow. Or like pitchers, right? Every single pitch in Major League Baseball, they tell you that the speed of it. Or most sports, they'll mention speed in some way. They've got trackers now on NFL players where they can track how fast they're running and all kinds of cool stuff. That's one of the most basic things we want to know, how fast. Well, if you don't want to know how fast something's going, you want to know its speed. Speed. Pretty basic. We studied this in junior high, right? To find the speed something travels, you would take the distance it travels divided by how long it takes to get there, right? So from one, the 100-yard dash, or 100-meter dash now, right? How long did it take to get 100 meters? You take the 100 meters, divide by the time it took, and you get meters per second, how fast it was going. You could translate that as well. Speed is simply defined as the distance traveled per unit time. Distance traveled per unit time. And of course, speed here in America, we use, well, sometimes, rarely. I mean, most of the time, miles per hour, right? Whether it's a fastball, whether it's a hit ball, car racing down the track, people running even, we generally think miles per hour. Now, the better unit would be, Michael, feet per second. If we're going to do a scientific study, feet per second gives us a better feel. And of course, in SI, there's really only one unit we're going to get to roll with, and that's meters per second. So put a star next to that. Most of our work will be in meters per second. Every now and then, I'll translate things, or we will translate things into feet per second, or certainly miles per hour, simply for our own reference, right? Because if I say Kendall was, running at a rate of 11 meters per second. Like, is that fast or not? I don't know. It is fast, right? You translate that out, it's about 20-something miles an hour. She's booking. Okay. So yeah, that is fast. But for our reference, sometimes it's hard to think that through. So these are our different units of speed. Now, speed is what we call a scalar quantity. A scalar quantity. In physics, there are two types of quantities, and one of them is a scalar quantity. A scalar is any quantity that has magnitude, but not direction. Any quantity that has magnitude, but not direction. Any quantity that has magnitude, but not direction. For instance, time. Does time have a direction? Not really, right? It's just hours. Like, not, there's this many hours going east. I mean, what? Right? Time doesn't really have a direction to it. Time is a scalar quantity. Speed, likewise, is a scalar. It doesn't really account for direction. Direction really doesn't matter as far as finding speed. But we also have quantities called vector quantities. And this should be a term you're familiar with, I believe, from your physical science days, correct? Vector quantities. Vectors are quantities that have both magnitude and direction. Quantities that have both magnitude and direction. For instance, let's go back to the edge of a sheer cliff. And Audrey's like, where's my branch? All right, Audrey stands at the edge of the cliff because she's a daredevil. Oh, she has one here. She's a daredevil like that. And she's like, I like to get as close to the edge as I can. And Kendall comes up behind her and applies a force of 100 pounds. She just saved Audrey's life by yanking her back from the edge of the cliff. You didn't think she'd push her, did you? Force is a vector. It has magnitude, but the direction very much matters, doesn't it, Audrey? If Kendall applies her 100 pounds of force the wrong direction, by Audrey and Audrey and Audrey, right? But if she applies it in the correct direction, she saves your life and she prevents a disaster of your foot slipping right there on the edge. You see how close you were? That was almost dangerous. Lucky for you, Kendall was there to save your life with her 100 pounds of force. vector has both magnitude and direction. And if we were to account for the direction of speed, we have a vector called velocity. Velocity. Velocity is speed in a particular direction. Velocity is speed in a particular direction. So for instance, I don't know if you've ever seen a football game. It doesn't happen very often. There have been a few times in recorded history, and it always makes highlight reels, where a running back is running and he gets spun around and starts running the wrong way. Or a defensive back collects a fumble and forgets which direction he's supposed to run. And so these things make highlight reels, and it's just because, oh, that was so funny, look what happened. Or a basketball player gets a defensive rebound, puts the ball right back up and scores for the wrong team. Great effort, right? Maybe the running back he's running it with great speed, but he's running in the wrong direction, right? The direction matters, right? So velocity, speed in a particular direction. Understand this then, since velocity as a vector has both magnitude and direction, if either of those things changes, the velocity changes. So if Kendall's running at 11 meters per second, you didn't know she was that fast. She's running 11 meters per second, and then she starts to slow down. Well, her velocity has changed because the magnitude changed. Or you thought she was blazing before. She's like, was it Dash in Incredibles? Right? Grace Christian School does not necessarily recommend any movies. But anyway, Dash in the Incredibles, right? She starts running that fast, okay? You didn't know she was a superhero kid. And her dad's like, I did because I'm a superhero. Anyway, he would say that too, wouldn't he? He would claim to be a superhero. Anyway, and so she starts running faster. Well, that's again a change in magnitude. So that's a change in velocity. But if Kendall just turns and starts running, she's going this way and she turns and starts going that way, that is also a change in velocity because part of her velocity has changed. Even if she's running at the same speed, if her direction changes, the velocity has changed. Does that make sense? Questions on that? All right, so a couple of types of velocity. We have, first of all, what's called uniform velocity. Uniform velocity. This would be you're driving through, say, Kansas on the interstate. Straight line, constant speed. You got it on cruise control. You may or may not be following the speed limit. We would certainly recommend following the speed limit, right? Obeying the laws of the land. I think God teaches that, so that's important. But you're going still very fast down the interstate, and there's absolutely nothing to go around. No towns, no cities, not even a tree or a rock to dodge. It's just wheat fields and cornfields everywhere in Nebraska, right? And occasionally a tornado. All right, anyway, so you're driving through Nebraska. For quite a long time, you'd be demonstrating a uniform velocity, correct? But if you try to drive through Columbus, Georgia, now every now and then you hit every light green. How many have you, and it's memorable, right? Like, I didn't get a single red light today. It's an amazing feeling, right? How many of you say, I cannot remember a single time that it's ever happened? I always hit red lights, and it's usually many of them. Okay, so you can't remember a time, okay? Most of the time, though, you start, you stop, and certainly in Columbus, you turn left, you turn right, you turn here, you turn there, right? You make a lot of turns. You can't exactly keep driving straight line through Columbus. So when the velocity is constantly changing, most motion admittedly demonstrates what's called a variable velocity. Most motion demonstrates what we call a variable velocity. Now, the problem is it's really hard to calculate what's going on as the velocity varies, right? Uniform velocity, that's easy. If everything just stays just exactly as it is, nothing ever changes, at least not for this duration we're looking at, that's really easy to calculate. It's the variable velocity that makes things kind of messy, but honestly, that's more common, isn't it? So what we're going to look at then is not so much the velocity at a particular moment in time, but we kind of want to look at the average, right? For instance, on a 12-minute run. Now, Michael has no memory of 12-minute run, do you? You were here in 8th grade, weren't you? Or was it 6th? Your sister was here in 8th grade. So have you ever done a 12-minute run?
Yes.
Yes. Not for me, but maybe for someone else. You two remember 12-minute runs, right? And Kendall's face says it all. I actually mentioned to Audrey, she was helping me with the last 12-minute run. It's like, bring back fond memories, Audrey. And she's like, yeah. And I was like, you glad you're on this side of the clipboard now? She's like, actually, I didn't mind 12-minute runs. I'm like, you're weird. Just No, I did running when I was in high school, like 10th through 12th grade, but I hated long distance running when I was in junior high, which was the years I had to do the endurance runs. So anyway, but endurance runs, in theory, you'd start off with a good steady jog and you would never deviate your speed at all, right? Perfect world. But reality kicks in and you get tired, you get a cramp, and you start walking, and then you're like, I shouldn't have walked. So you run fast, but that makes you tired, so you have to walk again. You speed up, you slow down all through the run, right? But at the end of the day, if I wanted to see, okay, how about this Kendall person? How did she do? I would take the total amount of distance that you traveled, divided by the total amount of time you spent, and we would say that was your speed, right? We call this average speed. Average speed is simply the total distance traveled divided by the total time. And when it all comes out, we say that Kendall was running at, let's just say, 7 miles an hour. You walked too much. Actually, I don't remember how your endurance runs went. Did you usually get hundreds, 90s?
I usually got A's.
A's, okay, so 90s, 95s. Sneak 100 in there every now and then. I don't have records that go back that far, so I really can't remember. It's back when you were just a young thing, shall we say. All right? Anyway, that's average speed, total distance divided by total time. Well, we could do the same with velocity, right? We could take the total, now wait a second, total distance traveled. Here's the hard part. Remember, velocity has to account for a direction. But imagine you're driving to school and you start here, and so you go this way and this way and this way and turn here, turn there, turn here, and you end up here. Now I get taking all that distance total and dividing by all the time total, but how are you going to average out the direction? You can't. So what physicists will do is we'll say, okay, we're going to take straight line. And we're going to allow that to dictate two things. First of all, it's going to dictate the direction. Now, if you were looking at this on a map, that would be southeast, correct? Okay, so our direction is, on average, southeast. But also, there's a lot of different routes you could take, right? How many of you, there's more than one route to get to school, so in case there's an accident, you go another route. This morning, I got donuts for the pre-cal students, and coming out of Golden Donut, I had just very unfortunate timing. There was a massive line of cars, and their light was just turning green for the other direction, so I knew I needed to get across the street quick, but there was no way to get into that line. So I cut through the line and took a different route to get to school. And I was like, yay, we're going the other way. And you know I like to do random voices, right? Just randomly change my accent for whatever reason. So the last time I went that route, apparently, and I don't perfectly remember this, but I used a Yogi Bear voice while we were going. How many know what Yogi Bear is? Okay, no, you do. Okay, just too lazy to raise your hand. All right, true mathematician there. All right, so I did a Yogi Bear voice. Yay, we're going the Yogi Bear way. Now, I didn't do a Yogi Bear voice today because I was too busy eating an apple fritter because it was still warm. It was great. Anyway, I'd never gotten a warm apple fritter from Golden Donut before. I will endorse Golden Donut, and I believe Grace Christian School would endorse them as well. So I will publicly endorse Golden Donut on my YouTube channel, in case anyone ever watches the video. But a warm apple fritter, like apple fritters are good anyway, but man, a warm apple fritter, that was so good this morning. So I was too busy to do a Yogi Bear voice. We don't call that distracted driving, by the way, just for record, since your dad's a cop. All right. Anyway, but there's other routes you could take, right? You could go this way and that way. Okay, we don't want to worry about any of that route that we're taking. So what we're going to say is, how far from point A to point B in a straight line? And you realize what that's going to do to your overall speed if you did that. It's going to drop because you inevitably travel further than that, right? We know the straight line is the shortest distance between 2 points. So whatever other path you could have possibly taken, which almost never is in a perfectly straight line, is going to be longer. We call this straight line distance displacement. Displacement. It's the straight line distance between 2 points. And it helps to define the direction of velocity. But that's what we have to rely on then to find what we call average velocity. Because average velocity is defined as the displacement, not the distance, but the displacement per unit time. So we would take the displacement you traveled from point A to point B per unit time. So you might have actually traveled 12 miles to get to school using the circuitous route of turning. But in a straight line, that same trip may have only been 7 miles. Well, 7 miles is what you get for your displacement. But again, it allows us to define our direction. And then we take however much time it took you and we figure your velocity from there. So this gives us our first equation, V sub AV, V for velocity. We've actually seen that. Have we seen that yet? V for velocity. Has that come up at all yet in this class?
Oh wait, yes.
Okay, I can't remember. I know capital V for volume has come up. I don't remember if we used lowercase v yet. Lowercase v is velocity, capital V volume. So V sub AV for average velocity is d over t, where d in this class is not distance, but displacement. D is not distance, but rather displacement. And that's how we can calculate average velocity. Average velocity. I do want to point this out. Direction can be defined a couple of different ways. And I think I've referenced this. Yeah, I referenced this, in fact, talking about restorative force in the last chapter, before your last test. And I mentioned that a negative sign indicates a change in direction, or rather an opposite direction. That's still going to be true. So going from home to school, if we consider this to be positive motion, then going from school to home would be considered negative. Now, you might think that's backwards. You might think going to school is negative and going home is positive. I guess it all just depends on your perspective. I think you going to school is positive because I get to see you. I don't get to see you at your house. Never mind, don't even think about it. Perish the thought. All right, so home to school will say it's positive, school back to home negative. But when you go in an opposite direction, that's negative. So for instance, a pitcher in baseball, right? If there's the plate, pitcher pitches the ball, to him that's positive velocity. And then if the ball's hit right back up the middle, negative velocity, especially if you can't get out of the way. Anyone ever watched it happen, like you're watching a baseball game and you watch it when the pitcher gets hit? Oh my goodness. It's one thing to watch the replay later. It's another thing because the shock factor. Usually if you're watching a replay, like you already heard that he got hit, that's why you're watching the YouTube on video, like, wonder what that looked like. When you're watching it live, you just don't expect that. Oh my goodness. And of course, you know, PEI pitch, and that does nothing for me at all. But anyway, ball right back up the middle. Well, that's negative velocity, whatever speed at which the ball's traveling, because it's going in the opposite direction it was before. Make sense? So we can use north, south, east, west, and things like that, southeast, to describe our velocity, or we could use positive and negative to show direction as well. And we'll do different ones for different things. I do want to mention, just because the book mentions, talks about instantaneous velocity. We can't do that in this class yet. In fact, we're going to save it for pre-calculus at the end of the year. We'll look at how to use calculus to find instantaneous velocity. But the motion has to be describable by a function. We'll look at all of that in pre-cal at the end of the school year. So for our purposes, we'll only really be concerned with this average velocity. Look at page 82, if you're not already there. And look at example 6.1. Read that for us, if you would, Michael. Page 82, example 6.1.
An arrow flies to a target exactly 205 meters away in exactly 2.5 seconds. A, what is its average velocity in meters per second? B, what is the average velocity in miles per hour? Neglect the curvature of the arrow's path.
All right, so again, we are going to assume rectilinear motion because we're also assuming a displacement, which is a straight line distance. So even if the path is curved, we don't care, because all we care about is point A, archer, point B, target. How far away are these two things? I don't care even the distance the arrow travels. He might have shot it up like this to hit the target. I don't care. He just overshot the target. Target is now here, all right? Anyway, I don't care what path it took. It went from point A to point B. What is that displacement? And what is the displacement, Michael?
205 meters.
205 meters. And it said it took how much time to travel that displacement, Michael?
2.5 seconds.
2.5 seconds. So to find the average velocity, class, we simply divide on your calculator. 205 divided by 2.5. And what is the average velocity of this arrow?
82 meters per second.
Comes out evenly?
Mm-hmm.
All right, 82 meters per second. Then it says convert this to miles per hour. And remember, to convert meters per second to miles per hour, we've got to use some dimensional analysis, don't we, right? We put this 82 meters per second as 82 meters over a second. And let's see, I can convert meters into feet because 1 meter equals, and that takes care of the meters, but I don't even want feet, I want miles per hour, right? So let's convert feet to miles. 5,280 feet, put that in the bottom to cancel, is a mile. All right, and then I don't want seconds, I want hours.
3,600.
3,600, let's see, I need to put that on the top again, over the 1 hour, and that cancels away the seconds. And so you can take the 82 that's already on your calculator, times 3.281, times 3,600, and divide that by 5,280. And how many miles per hour is this arrow traveling? And I think this may be slightly unrealistic. 183 miles per hour. Is that coming even? Surely not.
No.
Is it 2 sig figs or 3?
It's 2.
Oh, it's 3 sig figs. Okay, so this actually should have been 82.0 meters per second. And it came out to 180.
3.4.
3.4, blah, blah, blah. Okay, so hence we do round to the 183 miles per hour. All right, again, I'm not an archer, so I don't actually know how realistic that is, but it sounds a little fast for an arrow. I don't know. Maybe it's right. Any of you do bow hunting? Anyone ever shot a bow? I've shot one. I'm not a bow hunter, but I've shot one. All right, turn over to, or look across the page at example 6.2. Here's a fun one. Audrey, go ahead and read this one for us.
A bank robber ran out of the bank at 7.5 meters per second. The police officer attacked him 13.4 seconds later. How far was the robber from the bank when he was caught?
Good. By the way, I did want to point out, you said velocity. Doesn't velocity have direction? Yes, the direction is positive. It went the direction you wanted it to go. Okay? If it had pulled back and the arrow flew backwards, then we'd have negative velocity. Okay? So the positive is the direction in this case. Now, if they'd said that he shot at a target that was due west of him, then we would have said 82 meters per second west. But since it didn't give us a compass direction, shall we say, we just use positive and negative. We'll do the same thing here. It doesn't tell which direction the bank robber is running. All right, so let's see what it does give us. It tells us he runs out of the bank class at 7.5 meters per second. Well, that is his velocity, isn't it? Now, to him, positive 7.5 meters per second, right? And then he gets tackled 13.4 seconds later, class, that's time. And it says, how far was he from the bank? We're looking for his displacement. Good. Assuming he ran in a straight line. Now, if they're shooting at him, he'd be zigzagging, but he's just trying to get away, presumably running in a straight line. Now, my equation here is that average velocity is displacement over time. How would I solve the equation to get the d by itself, class? Multiply both sides by the t, right? Or cross multiply, you could say. So we're just going to multiply this average velocity times the time, and that'll give us the displacement of the bank robber. And what do we get here? Kendall?
100.5.
Okay, comes out evenly to that? All right, and then sig figs, is it 2 or 3? Oh, it's 3. This was 7.50, so we'll round off to?
100 meters.
Well, the 5 is gonna...
Oh, 101.
Yeah, 101 meters away from the bank. Positive 101 meters. All right, questions on that? And the book is incorrect, and don't worry about the equation they used. All right, questions on this? All right, turn over to page 93. Turn over to page 93. And look at problem number 2. Problem number 2. Go and read that for us if you would. Kendall.
An observer spots an airplane directly overhead at exactly 3:47 p.m. At exactly 3:59 p.m., the same airplane is spotted directly overhead by an observer 45 miles away. What is the speed of the airplane in miles per hour?
All right, the speed of the airplane. So we don't care about the direction or anything like that. We're just looking for distance divided by time. And it says, what distance did the plane travel in the problem class? 45 miles. That's his distance. And probably it was a displacement as well, probably, okay. And then the time it took. Well, it doesn't come right out and tell us, but it kind of does. Kendall, how much time did it take for the airplane to go those 45 miles? Stay with me. 12
minutes.
12 minutes. So if we were to calculate this out, we could say that the speed, which is distance over time, is 45 miles divided by 12 minutes. But we don't generally use miles per minute as an answer, do we? It says find it in miles per hour. So what should I multiply by to get miles per hour, class?
3600.
Careful, I have minutes. 60 minutes over the 1 hour. And that'll give me miles per hour. Go and find it very quickly at your seats. How many miles per hour is the plane traveling? And what do we get, class? 225. Now I'm looking at this, I'm like, how many sig figs do I have? Only 2 sig figs. So I'm going to have to round this off and say it's going about 230 miles per hour. All right, homework for this evening. Homework for this evening is to read. We'll read pages 85 to 89. Read pages 85 to 89. On page 93, answer question 8 and do problems 1 and 4. On page 93, answer question 8 and do problems 1 and 4. All right, have a wonderful rest of your day, and you are dismissed.